People vote based on their stances on issues, like the arrangements of produce and livestock on a farm. We've seen that there isn't much we can do to rearrange these stances to raise the general satisfaction with the election's winner above 50%. But we haven't taken a look at the priorities that voters assign to their stances. In our current model, these priority values are randomly assigned, such that it's possible for one voter to take a set of very high priority values and for another to take a set of very low priority values. But what if voters thought differently about their priorities? For example, it's difficult for a voter to consider every political issue as highly important. Aside from being emotionally tiring, it's just not the way the human brain works. Similarly, it's rare for a voter to be entirely apathetic and to have no high priority issues at all. A more appropriate model is for voters to assign higher priority to a fewer number of issues and a lower priority to a larger number of issues. This structure is sometimes called the cone of certainty. Now, some voters place such a heavy weight on the issue in the top of the cone that they won't consider any candidate that disagrees with them on that issue, regardless of how closely they agree on everything else. This approach is called single-issue voting. Today, we're going to model these two behaviors. The first practice we're going to look at is rescaling our issue priorities such that they aren't all quite so randomly distributed as they were before. So previously, our priorities were assigned as a random variable between 0 and 1. Then they're normalized by dividing the candidate match score by the total priority for each candidate. So there's a little bit of normalization for each voter, but there's not really a normalization in the sense that this random number generator can generate a whole lot of high values or it can generate a whole lot of low values. It's in general not going to do that, but there is a possibility that it will. So inside the generate issues subroutine, which gets called whenever we generate the voters, I've now added this section where we rescale the priority values. I've programmed in a few possible options. I've got the second two commented out. This first one is just going to rescale the priorities linearly. So what it's doing is it's keeping track of, for every issue, the number of issues that have a greater weighting than that one issue's priority. So back up here, we've added in this chunk where we're looping over all of the issues in issue list. We're comparing them against all of the other issues in issue list. And basically, if the second one has a higher priority than the first one, then this one's in greater value gets 1 added to it so that we can keep track of how many of the others have a higher priority than the current one. Which is pretty useful. So, for example, this gives us basically a ranking of them. Which one has none greater than it is going to be at the top, and the one that has the most greater than it is going to be at the bottom of the list. So here what we're doing is we're rescaling the values. So we're basically ditching the previous priority values, and we're just basing it off of the number that are greater than it, and we're doing this linearly. So when an issue is at the top, so it has none greater, then this value is 0. And so you have 1 minus 0 gives you 1, is going to be the highest priority value assigned to that issue. If you're at the bottom of the list, to where this is the nth issue, or really the n minus 1 issue, then this is 1 minus a number that's pretty close to 1, so it's going to be a very low number. So it scales it nicely from 1 down toward 0, but not quite reaching it, and making them evenly spaced. So the weightings are now going to be evenly spaced across the issues. Let's see, for example, how this works out, because we also do this in the candidates. So what I can do here is I've got a little script where, oops, not that part. Down here I've got a few lines that will print out the stance and not the stance. It'll print the issue number and then the priority assigned to it, so we can watch that. Assemble itself. There, that's the word I'm looking for. Let's see this thing reorder itself. So here we're going to be going through 50 years, so that's going to take just a couple minutes. And of course it's going to jump back down. But what you see from these priority values is that none of them are the same, and if you were to arrange them evenly, or if you arrange them in order, you'd see them go in these nice even increments. It looks like the lowest one goes down to 0.1, and the highest one, it looks like, yep, there is a 1.0 right there. Yeah, so it does go all the way up to 1. Okay, I will fast forward through this part while it runs through 50 election cycles. Alrighty, so we have worked through our rescaled priorities. So again, everybody's priorities are now evenly distributed between 0 and 1. That took a little bit longer to run because I've discovered that the imbalance we've been getting between our winners is largely due to the fact that even though we're iterating this over 50 cycles, or over a number of election cycles, it's still a small sample size compared to the parameter space. So what we've got currently is 50 years, and actually let's move in years up to here to where I can change it the same place as in dim and in issues and everything. So we've got 50 years, we've got 50 issues and 200 voters. I've discovered if I make those a little bit larger, even though it takes us a bit longer to run, it does tighten up this graph a bit. And it more consistently produces a balanced winning between the two candidates who are going to win. I set this one up to where we would have one dimension, so you ignore the second two leanings in these lists. And we've got two extreme candidates and two not quite so extreme candidates. As we've seen, the most extreme candidates take all the wins. And the population's still just above 50% happy. This has been 51% consistently, and doing this linear rescaling of the values doesn't seem to have changed that any. So let's now try a different rescaling. So that assumes that all of the values are distributed linearly. That's not really in line with the cone that we talked about earlier. A closer approximation would be to rescale these priorities quadratically. So in this case, we're taking the same structure we had before, only now we're squaring the thing that we're subtracting. So this thing is still going to go between 0 and 1, but it's going to tend to flatten out down near the... actually, I suppose this will flatten out near the top end, won't it? Well, we'll continue to give this... Oh yeah, actually, that is the way I want it to work out. Yeah, because then the higher priority stuff becomes less dense than the lower priority stuff. Okay, so let's see how this works out. Okay, so our quadratic scaling doesn't seem to have changed anything either. Population still on average about 51% happy. We're still getting the X formation. It hasn't really changed distribution all that much. So going from the linear to the square doesn't really seem to do a whole lot. The one I really want to take a look at is actually setting up a bona fide cone of certainty. Let me give you a picture of what this looks like. So you imagine, for example, that you get the priorities ordered in terms of their raw values. So say you have one that's 0.99, another that's 0.85, another that's 0.67, another that's 0.55, another that's 0.40, and another that is 0.25, and on. So you can imagine, you insert something in between there. This is plenty for now, though. What we want to do to make these into a cone is we want to assign them values based on where they fall in the order, and we want the binnings to get larger the farther we go down. So for example, this top one, we want that to be the only one that has a priority of 1, right? Or actually a priority of, let's just give the order first here, and then we'll figure out the priority. The next one, we want there to be 2 in there, and we want those to have the second highest priority. The next level, we want to have there be 3 in there, so that there's a third level of priority with 3 in them. And then you can imagine the next bucket is going to have 4, the bucket after that have 5, etc. And so in order to find out the actual priority value, So this is the one that we actually want, because we want this one to have a higher priority because it's number 1. So basically what we would do is we would take the highest priority value, whatever that is. So in this case, let's say there were only 6 issues, that would be a 3, and we would subtract 1. Here we would, actually no, we would not subtract 1, because if we follow that formula, then the one at the bottom is going to have 0 priority, and it does deserve some priority. So this one's going to have max priority minus 1. This one will have max priority minus 2, etc., etc. So for example, if we had 3 priority levels, this one would have priority of 3, this one would have priority of 2, this one would have priority of 1. If we had 10 priority levels, this one's going to get 10, 9, 8, 7, etc., all the way down. But the goal is to make the buckets we get to put these priorities into larger the farther we go down the list, so that the lower priority stuff gets lumped together. That's what this code keeps track of here. So the cutoff is basically the comparison you want for the number that's greater than it. So for example, this guy has 0 greater than it. So it's got a cutoff of 0. This one down here can have up to 2 greater than it, so its cutoff is 2. This one down here, it's got up to 3 greater than it, so its cutoff is 3. You notice that's also the level that they're at, except for this one doesn't quite match up, but I take care of that in just a second. So we've got the cutoff, we've got the priority, and we've got the maximum priority. So that's this the final priority that we have to keep track of down there. I called it Primax here and Max Pri over there. My bad. Primax makes me think of Prion, and now I want to play some Plague Incorporated. So we've got for issue in, issue list, we're looping over all of the issues, and we're basically checking for where that issue falls in terms of the priority level, in terms of which one of these buckets does it fall into. Is it less than or equal to the current cutoff and greater than the previous cutoff? If so, then we assign it its new priority. We update the maximum priority just in case. We increment the priority by 1. So again, the priority is this number here. We update that by 1. But then we update the cutoff by the priority value. So we go from having 1 to having 2 to having 3, etc. So each time we're adding on the number that we had before, which is pretty cool. So that gets them arranged in this nice cone structure, except that's getting the order reversed. So that's getting this in terms of 1, 2, 3, 4, 5, etc. And so this last part just takes care of flipping that around. This is the maximum priority minus the issue priority, and we add the 1 so that nobody has a 0 at the end of the day. This is so this, like I said, this is basically putting everything into that cone. Let's run it and see what it does to our population results. Okay, so the first thing we should check is the priority distribution. So if I did order this as a cone, then it should have just 1 up at the top. So let's see, where is the highest number? It looks like the highest number is 10. We only get 1 of those, right? So we only get 1 priority 10 value. Then we should get 2 number 9s in this list. So there's 1. And come on, 9. There's 2. No more, no more. Okay. And then we should get 3 8s. 3 8s. There's 1. And there's 2. Come on, show me one more. And there's 3. Awesome. Okay. So we've got this nice pyramid structure to our priorities. We've run 50 election cycles. It didn't, as you've probably come to expect by now, it didn't change our population's overall satisfaction. We do have a little bit better distribution of the wins, so that's a good thing to see. We go back up here, we were able to get these kind of fluke values where one won 60% of the time and the other 40% of the time. So that's interesting to see. The shape of the graph, again, pretty divided. Again, the folks over here are never feeling mediocre about it. The folks in here are never feeling terribly ecstatic or disappointed. So rearranging our priorities has not really changed the results all that much. It's gotten us a little bit more consistent 50% distribution, but it hasn't really done anything to the population satisfaction. So let's see what happens when we take a look at the second voting approach that we want to model today, and that is single issue voting. So this is a little bit different than arranging priorities. This approach says that there is some issue that a voter considers so important that they will not vote for a candidate unless they agree on that one issue. So it's if you've taken the GMAT, it's a necessary but not sufficient condition. In other words, they might match on that one single issue, but that doesn't necessarily guarantee that they will vote for them. It just says that if they do not match, it guarantees they will not vote for them. So the way we're going to set this up is we're going to set up a probability of single issue voting. This is the fraction of the population that is willing to single issue vote based on issue 1. So we're just going to take one issue for right now. We could expand it to include multiple issues, but for right now we're just going to say that issue number 1 is the hot button issue that people are going to single issue vote on. And let's reduce that to 0.1. So this means that 10% of the population single issue votes based on issue 1. Everything gets defined the same as it was before. We're still going to do one leaning, and we're going to do one, we're not going to do the prioritization of priorities, the rescaling of priorities, that's what I'm looking for. We're not going to do the rescaling of priorities just yet. I might combine that in a future episode. We've got the same randomized stances, but then what we're going to do is in the voter class, so where we generate the voter, we go through what we did just before, but we've added this block of code here. And this determines whether this voter is going to single issue vote based on issue 1. And so basically we pick a random number between 0 and 1. If that random number is less than the probability, then the SIV value, the single issue voting value, becomes true. Otherwise it is false. And so what we'll do is, if they are single issue voting, then we got to do two things. First of all, we have to put their stance in the direction of that leaning, right? Because the single issue voter is going to follow along with the leaning that they are proclaiming. And then we're setting the priority of that to be 1. Basically, the priorities are randomly generated between 0 and 1, not inclusive, meaning it will never come out to be 0, it will never come out to be 1, and so this automatically makes this the highest priority for this voter. But that alone is not enough, because this voter needs to reject any candidate that doesn't match that. So that means we need to make a modification to the match score calculation. So here we're looping over the voters, we're evaluating their match score. So we calculate the match score just like we did before. And here's where we check for the single issue voting condition. So if this voter is single issue voting, and if their stance on that issue, so again, well, it's issue 0, not issue 1, it's the first issue. If that doesn't equal the candidate stance, then we drop the match score for that voter and that candidate to 0 automatically. No questions asked, no further debates listened to. It is 0 automatically. They will not vote for that candidate. And so what that's going to do is it's going to make that candidate it's going to make that voter reject candidates more easily, or maybe easily is not the right word, more readily. There we go. And let's see here. Let's change this note to issue 0 so that I don't forget that later. Okay, so let's run this and see what we get. Okay, so we notice some things that we've observed before. Our extreme candidates are the only ones to win. Our not quite extreme candidates win 0% of the time. But one thing that's interesting to note, this average satisfaction has decreased. It's decreased a little bit, right? It's gone from like 51.5% to 50.5%. But since it's been so consistently, slightly above 50%, that for it to drop down like that is noticeable. It is a noticeable change in the performance of the code. we can test whether that's actually the case by increasing the percentage of voters who single issue vote. So let's up this to, you know what, let's go all the way to 30%. So let's say that 30% of the population is single issue voting based on issue 0. And let's see if that has let's see if that makes a stronger impact on the overall satisfaction rating. Okay, so we do see a correlation there. So we increased our number of single issue voters. The population is on average at a lower percent satisfaction rating, but also our standard deviation went up a little bit because, hello, you there? There we go. Because we're starting to get, because we're starting to get we're starting to get some of these dots dropping down from the top there. We're starting to get some more flattening out to 0 here. That's the effect of the single issue voting, reducing satisfaction scores to 0. Another interesting thing to look at is whether only 1/2 of the population is single issue voting. Let me show you what I mean by that. Currently, for when somebody is assigned or is determined to be a single issue voter, then they are voting in that they're voting in the direction of their leaning on issue 0. So what we can do is we can set it to where it's only the folks with a positive leaning are going to do single issue voting. So the folks with a negative leaning are not going to single issue vote, but the folks with a positive leaning are going to single issue vote. So they still have to be selected randomly for single issue voting, but it's only the folks who are taking the positive stance are going to take that. So this would be, say, you're taking this particular stand on this issue. Would you single issue vote? Whereas if you're taking the opposite stance, you wouldn't necessarily single issue vote. Let's see what that does to our results. Okay, so here's something interesting, is that the population satisfaction is still a little bit lower than it was before. What we notice is that there's now a greater imbalance in the wins. So now the positive ones, the ones who can potentially have single issue voting, are winning a greater percent of the time than the folks who don't have single issue voting. You can also see there's a little bit of an asymmetry to the graph here. This band going up and to the right is a little bit thicker than this band going up and to the left. So we've got a little bit asymmetry in the population there, as reflected by the asymmetry in the single issue voting practice. All right, let's test one last thing. This has all still been under the auspices of having 2 extreme candidates and 2 not quite extreme candidates. Let's see what happens when we've got no extreme candidates. So let's say we've got 2 folks with moderate leaning, so a 0.5 and a negative 0.5, and 2 folks with slightly more extreme leanings, but not all the way to the positive 1 or negative 1 level. Let's see what single... Now, previously, if you recall, John and Jim would have taken all of the votes, and Sue and Deb would have taken none, because the most extreme the most extreme candidates tend to win. But let's see what single issue voting does to those results. Okay, what we see is that the population satisfaction, again, lower, with again a little bit higher distribution of possibilities. The X formation has changed a little bit. We've got a little bit more sharply defined corners there. But what you notice is that even though John and Jim, who previously would have taken all the wins, they still take the majority, but now there's a chance for Sue and Deb to take the wins, because there's a probability that John or Jim won't take their their leanings stance on issue 0, which causes the single issue voters to reject them. Meanwhile, Sue and Deb could take the appropriate stance from for the single issue voters, and that causes the single issue voters to go to them instead of John and Jim. Even if John and Jim are closer matches for them, even if their match score were higher apart from the single issue voting, the single issue voting can cause their scores to go down to 0 for some voters, and for these to be, well, not 0, meaning higher than 0, meaning they get the votes instead of these folks. So What we've seen today is that the reordering of priorities doesn't really have that big of an effect on the results, but the single issue voting feature is the one thing that has made a dent in the results. For one thing, it's made it possible for some of these more moderate candidates to win when the more extreme candidates don't line up with the single issue voters' concerns, but that it also generally lowers this satisfaction rating here. So we finally found something that will make a dent in that satisfaction rating. So just as a reminder, all of the codes that we use for this series are available in the descriptions below. So the 2 codes that we've worked with today are available in the description below. I would love for you to download those, play around with them, see what type of results you can get, see what type of models you can create. Would love to see your results on that. You can post a link to it in the comments below, or hit me up on Twitter at Let's Code Physics. Thanks so much for watching. I will see you next time. Bye-bye.